Tonight, drift with me to the outer parts of our solar system, where giant planets rule and small worlds circle them in silence. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Now picture the sun shrinking behind you as we move outward, past the red dust of Mars, past the wide gray belt of asteroids, until the light fades to a soft, faraway glow. Out here, the planets are enormous. Jupiter is a striped sphere wider than 11 Earths set side by side. Saturn floats inside its pale rings, calm and slow. Uranus is a smooth blue marble tipped on its side, and Neptune is darker, deeper, the color of a winter sea at dusk. These giants are the loudest voices in the outer solar system, yet the mystery we are following tonight does not live on the giants themselves. It lives on the quiet little worlds that orbit them. Each of these huge planets has a family of moons. Some are tiny, just lumps of rock, the size of a small town. Others are larger than the planet Mercury. There are more than 200 known moons circling the planets of our solar system, and most of them are still barely studied. We have flown past a few. We have mapped some in faint detail. Many remain blurred dots in our best photographs, waiting patiently for a closer look. What makes these distant moons so interesting is hidden beneath their surfaces. From the outside, most of them look frozen and still. Their skins are pale ice, cracked and scarred, sometimes dusted with dark grit. The temperatures on the surface are far below anything you have ever felt. A walk on Europa, one of Jupiter's bright moons, would freeze your breath into glittering crystals before it left your mouth. A standing pool of water could not exist there for even a moment. And yet, under that frozen shell, something remarkable might be waiting. Slowly, over the last few decades, evidence has gathered that several of these moons hide vast oceans of liquid water beneath their ice. Not small pools, not damp layers, whole hidden seas, dark and deep, possibly larger than all the oceans on Earth combined. We cannot see them directly. We can only read their fingerprints in the wobble of a moon, in the spray of a geyser, in the faint tug of gravity measured by a passing spacecraft. The open question that pulls us in tonight is simple to ask and very hard to answer. Could any of these hidden oceans hold life? And if they do, how would we ever know, separated from them by hundreds of millions of miles and many layers of ice? There are several candidates worth wondering about. Europa, with its smooth, fractured shell. Enceladus, a small, bright moon of Saturn that throws plumes of salty water into space. Titan, larger than the planet Mercury, draped in a thick orange haze and dotted with cold lakes that are not made of water at all. Ganymede, the largest moon in the solar system, which seems to carry its own buried sea. Callisto, scarred and patient. Even Triton, far out at Neptune, where geysers may still whisper through the cold. Each of these worlds offers a different theory of what a hidden ocean might be like. Some researchers believe Europa is the most promising because its ocean may touch a warm, rocky floor. Others argue Enceladus deserves the top place because we have already flown a spacecraft straight through its plume and tasted what came out. A few wonder whether Titan, with its strange chemistry, might host life that does not need water at all. None of these ideas has won. The debate is gentle and ongoing, the way all good questions are. For now, simply let the scale settle around you. A handful of small moons scattered across the cold outer dark, each one possibly carrying a sea older than anything on Earth. No sunlight reaches those buried waters. No wind moves across them. If anything swims there, it has never seen a star. We will spend the next many hours wandering from moon to moon, sitting with the evidence we have and noticing what we still do not know. The point is not to solve the mystery tonight. The point is to rest inside it, to imagine those quiet seas, hidden under ice, holding their secret patiently while you breathe slowly, while the room grows still, while the giants of our solar system turn in the dark, carrying their small, frozen children with them. Before we wander out among the icy moons, it helps to pause and ask a simple question. What do we even mean by the word life? It seems like an easy word. We use it every day. Yet, when scientists try to write down a single clean definition, the words slip away like water through open fingers. the most common answer goes something like this. Life is a system that takes in energy, grows, responds to its surroundings, and makes more of itself. A blade of grass does these things. So does a beetle. So does the bacterium living on the underside of a wet stone. Each of them pulls in fuel from the world around it, builds copies of itself, and slowly changes across long stretches of time. Already, even with that gentle definition, the edges start to blur. A flame takes in fuel and grows and spreads, yet we do not call it alive. A crystal in a quiet cave grows in beautiful patterns, yet it does not seem alive either. A virus copies itself, but only by borrowing the machinery of another cell. So we are left with a soft, fuzzy idea. Life is something that does many things at once, in a way that keeps going, in a way that learns. On Earth, every living thing we have ever studied shares a few basic traits. Each one is made of cells, those tiny soft bags of salty water with thin skins around them. Each one uses long, twisted molecules to carry instructions. We call these molecules DNA and RNA, and they act like quiet little books of code. Each one runs on chemistry, mixing simple ingredients to make heat, motion, and growth. The ingredients themselves are surprisingly humble. Carbon, hydrogen, oxygen, nitrogen, a sprinkle of phosphorus, a dash of sulfur. These are some of the most common elements in the universe. They drift through clouds of gas between the stars. They settle into the crusts of planets. They wash through the oceans of small icy moons. The stuff of life, in other words, is everywhere. Liquid water seems to be the part that matters most. Not ice, not steam, but the liquid form that flows and dissolves and carries small things from place to place. On Earth, wherever we find liquid water, we find life. In hot, acid pools, in freezing, salty lakes hidden under glaciers, in dark cracks deep below the seafloor, where no light has reached for billions of years. This pattern is one reason researchers stare so hard at the moons of the outer planets. Many of those moons appear to hide oceans of liquid water beneath their frozen shells. Energy is the other quiet need. Living things must have some source of power, some flow of warmth or chemistry they can tap. on the surface of Earth, that source is mostly the sun. But far from the sun, in the deep dark of the outer system, sunlight is faint and thin. Any life out, there would need a different fuel. Heat from a moon's rocky core, perhaps, or chemical reactions between water and stone, or the slow squeeze of gravity from a giant planet nearby. When scientists talk about hunting for life beyond Earth, they often use a careful phrase. They say they are searching for biosignatures. A biosignature is a sign, a hint, a fingerprint left behind by something living. It might be a strange mix of gases in the air. It might be a pattern of molecules that chemistry alone would not easily make. It might be a shape in the rock that looks suspiciously organized. None of these signs on their own would prove anything. They would only raise the question and pull more eyes toward that quiet world. There is also a deeper worry hidden inside the question. We only have one example of life to study, and that example is us, along with everything else on this single planet. We do not know if life always has to use DNA. We do not know if it always has to use water. We do not know if it always has to use carbon as its main building block. Some researchers wonder if life elsewhere might run on different chemistry entirely. Others suspect that the recipe we know on Earth is the only stable one in the universe. Both views remain open. So when we ask whether life hides beneath the ice of a distant moon, we are really asking several smaller questions at once. Is there liquid water there? Is there a steady flow of energy? Are the right, simple ingredients present? And hardest of all, has nature found a way, in that cold, quiet place, to weave those ingredients into something that grows and copies and endures? To understand Europa, we have to travel back to the very young days of our solar system. The sun had only just begun to shine. Around it spun a wide, flat disk of gas, dust, and tiny grains of ice. From that disk, the planets slowly came together, piece by piece, over many millions of years. Jupiter formed early, and it formed huge. As it grew, it pulled in great amounts of material from the disk around it, and a smaller disk began to spin around Jupiter itself. That smaller disk would one day become its moons, Europa was born inside that swirling cloud of gas and dust. Bits of rock and ice drifted together, pulled by gravity, sticking and clumping into a growing world. Over time, the heavier rocky pieces sank toward the center, and the lighter icy pieces floated outward. This is how Europa came to have layers. Much like an onion, a dense rocky core sits at its heart. Around that core, a deep layer of water formed, and on the outside, a hard shell of ice wrapped the whole thing in a smooth, pale crust. The strange and beautiful part is the water in the middle. Europa sits far from the sun, in a region so cold that almost everything freezes solid. By all reason, its ocean should have turned to ice long ago, and yet the best evidence we have suggests that beneath the frozen shell, a vast salty sea is still liquid today. Some estimates suggest it holds more water than all the oceans of Earth combined. How can that be, so far from any warmth? The answer most researchers favor has to do with Jupiter itself. Europa moves in a slightly stretched path around its giant parent. As it swings closer, Jupiter's gravity pulls harder on it. As it swings farther, the pull eases. This steady squeeze and release flexes the moon from the inside, like a ball being gently kneaded by unseen hands. That flexing creates heat deep within the rock and the water. The process is called tidal heating, which simply means heat made by the pulling of gravity rather than the warmth of a star. This is one leading idea, but it is not the only one. Some researchers wonder whether Europa's rocky core also holds radioactive elements that slowly release warmth as they decay. Others suggest that the ocean may have stayed liquid partly because of salts dissolved within it, which lower the freezing point. Most likely, several effects work together. The exact balance remains an open question, and the answer matters because it tells us how stable that hidden ocean has been over time. The age of the ocean is its own quiet puzzle. If Europa formed roughly 4.5 billion years ago, alongside Jupiter, has its sea been liquid that whole time? Or has it frozen and thawed in long, slow cycles, depending on how stretched its orbit happened to be in any given era? Some models suggest the ocean has been continuous for billions of years. Other models suggest it may have come and gone. We do not yet know which picture is closer to the truth. What we can say is that the ice shell above the ocean is young, at least on its surface. When scientists look at images of Europa, they see very few craters. On most worlds, craters pile up over billions of years, like footprints in soft snow. Their absence on Europa suggests the surface has been reshaped, perhaps many times, by ice slowly turning over from below. The shell may be only tens of millions of years old in its current form, even though the moon itself is far older. That hints at a world still alive in some quiet geological way. Picture Europa as it likely looks from above. A smooth, pale globe, the color of cream and rust, marked by long, dark cracks that stretch across thousands of miles. There are no tall mountains, no deep canyons. The surface is one of the flattest in the solar system, polished by ice that flows and refreezes. Beneath your feet, if you could stand there, the ice might be several miles thick. And beneath that ice, in total darkness, a salty ocean rolls in slow tides driven by Jupiter's pull. How that ocean came to be and how it has lasted sits among the most patient mysteries in our cosmic neighborhood. Tidal heating, radioactive warmth, dissolved salts, and time itself all play some part. Which part matters most is still being worked out. For now, it is enough to picture that hidden sea, dark and quiet, a place that may have waited unseen since the planets first formed. If you could drift in close to Europa and let your eyes adjust to its pale, frozen face, you would see something strange. The whole moon is wrapped in a web of long, dark lines. They cross and curve and double back. They run for hundreds, sometimes thousands of miles, like cracks in old porcelain. Some are straight and sharp. Others bend in slow arcs that follow the moon's gentle curve. No mountains rise above them. No deep canyons drop below them. The surface is nearly as smooth as a billiard ball, marked only by these dark seams. Those lines are the building blocks of the mystery. They are made of ice, of course, but the dark color tells us that something else is mixed in. Something stained the ice from below, or from above, or from both. what stained it may be the key to whether anything lives there. The ice itself is mostly water, frozen so hard that it behaves like rock. At Europa's surface, the temperature sits near minus 260 degrees Fahrenheit. At that cold, water ice is brittle and pale and slow to change. But pressed into that ice in faint amounts are other things: salts, sulfur compounds, traces of carbon, possibly clays. Spacecraft have measured these from far away by reading the colors of sunlight that bounce off the surface. The readings are not perfect. They tell us roughly what is there, but not in what shapes, or in what amounts, or whether any of it is alive. One idea is that these stains rose from below. If a deep ocean lies under the ice, and if that ocean touches a rocky seafloor, then minerals can dissolve into the water. Warm currents could carry that salty brew upward into cracks in the shell, where it freezes near the surface and leaves a dark smudge behind. In this view, the lines on Europa are like windows. Looking at them is, in a small way, looking at the ocean itself. Another idea is that much of the staining came from outside. Europa sits inside the strong magnetic field of Jupiter. That field sweeps charged particles around the planet at tremendous speed, and those particles slam into Europa's surface day after day, year after year, for billions of years. They break apart molecules. They cook the ice. They can build new compounds out of the old ones, including sulfur compounds that drift over from a nearby moon called Io, which is the most volcanic world we know. So some of the color may be ocean chemistry from below, and some may be space weather from above. We do not yet know the balance. This is where the story stretches out and touches the rest of the universe. The water in Europa's ice did not begin at Europa. Most researchers believe the water in our solar system came from the same cloud of gas and dust that made the sun. Some of it may have ridden in on icy comets and small bodies, scattered by the gravity of the young giant planets. The water in your glass tonight and the ice on Europa may share that distant origin. The salts and metals have an even older story. Iron, calcium, magnesium, sodium. These did not exist when the universe began. They were forged inside stars in slow nuclear furnaces and then scattered into space when those stars died. Every grain of salt on Europa, every fleck of mineral, every atom of sulfur was made inside a star that lived and ended long before our sun was born. The dark lines across that frozen face are, in a sense, written in stardust. If life exists there, it would be built from those same recycled ingredients: carbon, hydrogen, oxygen, nitrogen, the same handful of elements that make up the trees outside your window and the cells inside your body. That shared chemistry is one reason the icy moons feel so interesting. They are not made of strange, exotic material. They are made of the familiar. What remains unknown is how those ingredients are arranged down in the dark water. They might be sitting in plain, salty brine, doing nothing in particular. They might be feeding slow chemical reactions on a warm seafloor. They might already be folded into something we would call alive. The cracks on the surface hint that the ocean and the ice talk to each other, that material moves between them, that the moon is not frozen still. But hints are not answers. For now, we can only watch the dark seams crossing that pale globe and wonder which of them, if any, is a faint signature written from below. The building blocks are there. Whether anything has built with them is the question we cannot yet answer. Far out in the orbit of Saturn, a small white moon turns slowly in the dark. Its name is Enceladus, and it is barely 500 kilometers across. You could fit it inside a single country on Earth. By every reasonable guess, a moon this small should be cold and dead. It should have lost its inner heat long ago, the way a stone left out at night gives up its warmth. And yet Enceladus is not quiet at all. From cracks near its south pole, it sprays great curtains of icy mist into space. These cracks are called tiger stripes, and they run almost parallel across the southern ice. They are warmer than the surrounding surface. Out of them rise tall, ghostly plumes of vapor and tiny frozen grains. The plumes climb hundreds of kilometers above the moon, far beyond what its weak gravity should allow them to do. Some of that spray falls back as soft snow. Some of it escapes entirely and feeds one of Saturn's outer rings. slowly breathing itself into the space around it. The question is, what is squeezing it hard enough to make this happen? The leading idea is tidal heating. Enceladus orbits close to Saturn, and Saturn's gravity is enormous. As the moon moves along its slightly stretched, oval-shaped path, the giant planet pulls on it harder at some points than at others. The moon flexes. Its rocky core bends just a little. Its ice shell shifts. That endless flexing creates friction deep inside, and friction makes heat. Imagine bending a paperclip back and forth until it grows warm in your fingers. Now, imagine doing that for billions of years. There is a second helper in this story. Enceladus is caught in a gentle gravitational tug-of-war with another moon, Dione, which orbits farther out. Their paths are locked in a quiet pattern where Enceladus completes 2 orbits for every one of Dione's. This pattern keeps Enceladus from settling into a perfectly round orbit. Without that nudge from Dione, the flexing might fade. With it, the heat keeps coming. The moon stays alive in a strictly geological sense, because 2 worlds are pulling on it at once. How much heat is enough is still a question. Some researchers think tidal forces alone can explain the warmth pouring out of the South Pole. Others suspect the moon's rocky core is unusually soft and porous, soaking up the flexing like a wet sponge and giving off even more heat than simple models predict. A third possibility is that radioactive elements deep in the core add a small, steady warmth of their own. The slow decay of heavy atoms left over from the moon's birth. Most likely, several of these forces work together. The exact balance is not yet settled. What we can say is that the heat seems to keep an ocean of liquid water under the ice. Not a slushy pocket, a whole global sea sloshing quietly beneath a frozen shell. The plumes appear to come straight from that ocean, finding their way up through cracks in the ice and erupting where the shell is thinnest. Each spray is, in a sense, a sample of the hidden sea, lifted gently into space for anyone passing by to taste. There are still open questions about how those plumes actually work. One idea is that the cracks reach all the way down to the ocean, and pressure from below pushes the water up like a slow fountain. Another suggests that pockets of brine sit trapped within the ice itself, and the plumes come from those shallower reservoirs rather than the deep sea. The two pictures lead to different chemistry and to different chances of finding signs of life. We do not yet know which is closer to the truth. The radiation around Saturn adds another layer to the puzzle. Charged particles trapped in the giant planet's magnetic field strike the surface of Enceladus constantly. This radiation can break apart molecules on the ice, creating new chemistry that may slowly drift downward. Whether any of it reaches the ocean below is unknown. If it does, it could feed reactions that life, somewhere down there, might use. So Enceladus turns in the cold, pulled by Saturn, tugged by Dione, warmed from within by forces we are still measuring. A tiny world that should have gone silent long ago, and somehow has not. The plumes rise, the ocean stirs, and the question of what, if anything, swims in that hidden dark sea waits patiently, hundreds of kilometers below an ice shell, while the moon keeps quietly breathing. Hold the image of Enceladus in your mind for a moment longer. It helps to know just how small this little moon really is. Enceladus is about 500 kilometers across. That is roughly the width of the state of Arizona, or the distance from London to Edinburgh. If you set Enceladus down on the surface of the Earth, it would not even cover the western United States. Our own moon is 7 times wider. Earth is 25 times wider still. A world that small should be cold and dead. That is what we expected. Small bodies cool quickly. They lose their inner heat to space and freeze through, all the way down. A pebble cools faster than a boulder. A marble cools faster than a stove. Enceladus, by every rule we knew, should have been a marble of ice, quiet and finished, drifting in the dark. And yet, near its south pole, water sprays into space. Try to picture the scale of that spray. The plumes rise hundreds of kilometers above the surface on a moon only 500 kilometers across. That is like a fountain on Earth that shoots water from the ground all the way up past the cruising height of every airplane, past the edge of the atmosphere and out into orbit. The fountain is taller than the world it stands on. Some of that water never comes back down. it escapes into space and joins one of Saturn's faint outer rings, a wide, pale band called the E-ring. That entire ring, thousands of kilometers across, is being fed by a single small moon. The ring is, in a sense, the breath of Enceladus, exhaled slowly for as long as we have been watching. Now think about the ocean underneath. We believe the water layer beneath the ice may be around 10 kilometers deep in places. That is about the depth of the deepest trench in Earth's seas. On a body the size of Arizona, an ocean that deep is enormous in proportion. If you scaled Enceladus down to the size of a beach ball, the ice shell on top would be thinner than a sheet of paper, and the hidden ocean beneath it would be a thin film of salt water wrapped around the whole ball, tiny, fragile, and entirely sealed away from the sky. Hold the distance in your mind too. Enceladus orbits Saturn, and Saturn is on average about 1.4 billion kilometers from the Sun. Light from the Sun takes more than an hour to reach it. By the time that light arrives, it has thinned out so much that Enceladus receives roughly 1% of the sunlight that Earth does. Standing on its surface, the Sun would still be the brightest thing in the sky, but small, a sharp, bright point rather than a warm disk. Noon there would feel like deep twilight on Earth. The ice would glitter faintly. Saturn would loom huge and pale on the horizon, its rings cutting across the sky in a thin silver line. In that distant, dim, freezing place, the surface temperature drops to around minus 200 degrees Celsius, cold enough that a cup of boiling water would not just freeze, it would shatter into glass. And still, beneath the crust, liquid salt water moves. Still, the plumes rise. Still, something keeps the inside warm enough for chemistry to happen. How much warmer, we do not fully know. Some models suggest the seafloor of Enceladus might reach temperatures close to those of the ocean floor on Earth. Others suggest it is much cooler, only just warm enough to keep the water liquid. Both pictures are possible. Both are being studied. The honest answer is that we have measured the spray, but not the floor, and a great deal still hides in between. There is a strange comfort in these numbers. A moon you could drive across in a long day. An ocean wrapped around it like a thin shell. Plumes taller than the moon itself. A faint pale ring stitched together from its lost water. And somewhere inside, a chemistry we cannot yet read. It is easy, when we talk about space, to lose the sense of scale. Billions of kilometers, billions of years, the numbers blur. But Enceladus is small enough to picture. You could imagine holding it in your cupped hands, a snowball the size of a small country, leaking salt water between your fingers, the spray drifting off into the dark. Whether anything inside that snowball is alive remains an open question. The scale only deepens it. A world this small should not be doing any of this. And yet it is, quietly, patiently, for reasons we are still trying to understand. Now we drift outward, away from the bright spray of Enceladus, toward a much larger and stranger moon. Titan circles Saturn at a slow and stately pace, hidden inside a thick orange haze. It is the second largest moon in our solar system, bigger than the planet Mercury. And it is the only moon we know of that wears a real atmosphere, dense and heavy and full of secrets. Imagine you could float just above its clouds. You would see no sharp blue sky, no clean white light. The air above Titan glows in shades of butterscotch and amber, soft and golden, like sunlight passing through honey. The haze is so thick that for many years we could not see the surface at all. Our telescopes met only that orange veil, smooth and unbroken, hiding everything below. Then, a small probe named Huygens drifted down through the clouds in 2005. It took pictures as it fell, and for the first time, the veil parted and we saw the ground. What it showed us was a world that felt strangely familiar and deeply alien at the same time. The sky overhead was a pale tangerine. The horizon faded into a soft brown blur. The ground below looked like a dry riverbed, with rounded pebbles scattered across a dark plain. The pebbles were not stone. They were lumps of water ice, frozen so hard at minus 290 degrees Fahrenheit that they behave like rock. Beneath your boots, the surface would crunch softly, a thin crust over damp, dark sand. If you walked across that plain, you would notice the gravity is gentle, only about 1/7 of Earth's pull. Each step would carry you farther than you meant to go. The air would press against you with more weight than our own atmosphere, thick and slow, and it would be very, very cold. Cold enough that water on Titan plays the role our rocks play here. Frozen oceans of ice form the bedrock. The dark sand beneath your feet is not sand as we know it. Researchers think it is made of tiny grains of organic material, soot-like particles that drift down from the orange haze above. Over long ages, these particles settle, gather, and form vast dunes near the moon's equator. From orbit, those dune fields look like long, dark ripples, hundreds of miles across, combed by slow winds. Some scientists wonder if Titan's dunes could rival the great deserts of Earth in size. Above all of this, the weather moves in slow motion. Methane clouds gather in the upper sky, pale and drifting. Sometimes they release a gentle rain, not water, but liquid methane and ethane, falling in fat, slow drops through the thick air. The rain may take many minutes to reach the ground. When it lands, it cuts channels into the icy bedrock, carving river valleys that wind across the plains. From above, those channels look almost exactly like the riverbeds of Earth. Same branching shapes, same gentle bends, made by a fluid that here would freeze us solid. The colors of Titan's surface shift as you travel. Near the equator, the dunes are deep, dark brown. Toward the poles, the ground grows paler, dusted with bright patches of cleaner ice. And at the very top and bottom of the moon, the land opens into something stranger still, wide, smooth, dark mirrors of liquid. We will sit with those in the next section. For now, picture them as distant glimmers on the horizon, calm and black under an orange sky. What remains unknown is what is happening beneath all of this. Many researchers suspect that under Titan's icy crust, far below the methane rivers and the organic dunes, there lies a deep ocean of liquid water mixed with ammonia. If that ocean exists, it could be 100 miles deep or more. But we have not touched it. We have not seen it. We only have hints from the way Titan's shape shifts as it orbits. Hints that something soft and yielding lies beneath the hard shell. So Titan offers us two mysteries stacked on top of each other. There is the surface itself, with its strange chemistry of methane and organic soot, where the building blocks of life seem to swirl in cold abundance. And there is the buried ocean below, sealed away under miles of ice, possibly warm, possibly salty, possibly stirring with chemistry we cannot yet imagine. Which layer, if either, might cradle something living? We do not know. We can only stand in our minds on that dim orange plain and look up at the soft, hazy sky and wonder what is hidden in the quiet world beneath our feet. On Titan, the lakes do not shine the way ours do. They do not catch sunlight in the same bright way, and they do not ripple in the same restless rhythm. They lie still and dark and slow, pooled in basins near the moons far north and south. And what fills them is not water at all. The lakes of Titan are made of liquid methane and ethane, the same chemicals we burn for fuel here on Earth, kept in liquid form by the deep, steady cold. This is what makes Titan so strange and so quietly fascinating. It is the only other world we know of where stable liquid pools sit openly on the surface. Earth has its oceans. Titan has its lakes, but the chemistry is reversed. On Earth, water flows and methane is a gas. On Titan, methane flows and water is locked away as ice, hard as stone. The largest of these lakes have been mapped from orbit by a spacecraft that swung past again and again, peering through the haze with radar. Kraken Mare is the biggest of them, wide enough to swallow some of Earth's great lakes whole. Ligeia Mare and Punga Mare lie nearby, smaller, but still vast. Their shorelines curve and bend in soft, fractal shapes. Rivers seem to feed them. Smaller ponds dot the land between, like quiet eyes looking up at the orange sky. What lies beneath the surface of these lakes is one of the gentler mysteries in our solar system. The lakes may be shallow in places, only a few meters deep, but in the deeper basins, the methane may reach down hundreds of meters. The bottom could be soft, layered with sludge, where heavier organic molecules have settled out of the air over millions of years. Some scientists picture a kind of seafloor coated in a slow, sticky residue. Others suspect the bottoms are crusted with ices we have not yet identified. Then there is the question that hangs over all of it. Could anything live in such a place. Liquid methane is a strange medium for life. It does not dissolve the kinds of molecules water dissolves. The chemistry would have to work in a different way, with different bonds and different rhythms. One idea, suggested years ago by a small group of researchers, is that life in methane lakes might use cell membranes made not of fats, as ours are, but of nitrogen-rich molecules that hold together in the cold. They called these imagined cells azotosomes. It was only a thought experiment, a sketch on paper, never proven and never disproven. A competing view holds that liquid methane is simply too cold and too quiet to support any chemistry complex enough to be called alive. The reactions that drive life on Earth need a certain amount of energy, a certain flexibility in how molecules bend and break. At the temperatures of Titan's lakes, around minus 180 degrees Celsius, everything slows almost to a standstill. Some chemists argue this slowness is a barrier no kind of life could cross. Both views remain open. Neither has been tested. We have flown past Titan, dropped a small probe through its sky, and watched its lakes from orbit, but we have never sailed one. We have never lowered a sensor through that dark methane surface to see what drifts in the deep. There is something else hidden beneath Titan as well, beneath the rocky icy crust, perhaps 100 kilometers down. Many researchers believe there is a global ocean of liquid water. Salty, dark, and pressed between layers of ice. It would have nothing to do with the methane lakes above. It would be a separate world inside the world. And if life exists on Titan at all, it might live there, in that hidden sea, rather than in the cold pools on the surface. So Titan offers us two possible places to wonder about: the strange lakes on top, with their inverted chemistry, and the buried ocean below, more familiar in its ingredients, but harder to reach. Which one, if either, holds anything alive? We do not know. We cannot yet know. The lakes themselves move very slowly. Winds on Titan are gentle. Waves, when they form, may rise only a few centimeters, traveling in long, lazy swells across the dark surface. Rainfall is rare, and when it comes, it falls as methane drops in slow motion, drifting through the thick air. Whole seasons pass between storms. For now, the lakes wait. They have been waiting for a very long time, and somewhere in their stillness, or in the deeper ocean beneath the crust, the answer to one of our quietest questions may simply be lying there, undisturbed, until we come close enough to look. Ganymede is the largest moon in our solar system. It is bigger than the planet Mercury. If it orbited the sun on its own, we would call it a world without hesitation. Instead, it circles Jupiter in a slow, steady rhythm, taking about 7 Earth days to complete one loop. That gentle pulse of orbit is one of the cycles that may keep its hidden ocean alive. Beneath a thick crust of ice, Ganymede appears to hold a vast layer of salty water. Some estimates suggest this ocean may contain more water than all the seas on Earth combined. We cannot see it. We cannot touch it. The evidence comes from faint signals, careful measurements, and patient reasoning. Yet, most researchers now agree that something liquid moves under that frozen shell. The rhythm of Ganymede is tied to its neighbors. It dances with Europa and Io in a pattern called a resonance, where their orbits lock into simple ratios. For every one loop Ganymede makes, Europa makes 2, and Io makes 4. This slow celestial waltz tugs at each moon in turn. The pulling stretches and squeezes their interiors, generating warmth deep inside. On Ganymede, that warmth may be just enough to keep the ocean from freezing solid. The structure of the moon, as best we can guess, is layered like a frozen onion. A small iron core sits at the center. Around it lies a mantle of rock. Above that, an ocean of salty water. And above the ocean, a thick crust of ice, perhaps over 100 miles deep. Some models suggest the ocean and ice may even be stacked in alternating layers, with different kinds of ice forming at different pressures. If true, Ganymede's interior would be a sandwich of liquid and solid, each layer shaped by the steady squeeze of gravity. That sandwich structure raises a quiet problem. If the ocean is trapped between 2 layers of ice, it may not touch the rocky mantle below. On Earth, life often draws energy from minerals where water meets stone. Without that contact, Ganymede's ocean might be cleaner, but also lonelier. One theory holds that warm, salty water could still slip through cracks and reach the rock now and then. Another view suggests the ocean sits sealed away, cycling its own chemistry in slow, isolated turns. We do not yet know which picture is closer to the truth. Ganymede is also the only moon known to make its own magnetic field. Inside that liquid iron core, currents flow and turn, creating an invisible bubble around the moon. This field interacts with Jupiter's much larger one, producing soft auroras at Ganymede's poles. By watching how those auroras rock back and forth, researchers found their best evidence for the buried ocean. The salty water responds to Jupiter's magnetic pull, dampening the wobble of the auroras in a way only a conductive liquid could explain. The cycle of those auroras, swaying slowly with each orbit, became a kind of message from a sea we have never seen. Time moves differently on a world like this. The surface above is ancient, scarred by craters older than most things on Earth. Grooved terrain stretches across wide plains, hinting at slow shifts in the crust long ago. Whether those shifts still happen today remains an open question. Some researchers think Ganymede's geology has gone quiet, its inner motions slowed to a near stop. Others suspect that the tides from Jupiter still stir the ocean below, even if the surface gives little sign. The argument is not settled. If life exists in that buried sea, it would live by rhythms we can barely imagine. No sunlight reaches it, no day or night, only the steady tug of Jupiter, the slow turn of the moon, and perhaps the gentle flow of warm water rising and falling in long, patient cycles. Any creatures there would mark time not by light, but by pressure, by chemistry, by the slow drift of currents in a dark ocean. A spacecraft called JUICE is now on its way to study Ganymede in detail. It will arrive in the early 2030s, slip into orbit around the moon, and listen for what the ocean has to say. It may measure the thickness of the ice. It may map the magnetic field with greater care. It may even spot small changes that hint at activity below. What it almost certainly will not do is answer the deepest question, whether anything lives in that hidden sea remains. For now, a quiet possibility carried by the slow turning of a giant moon around a giant planet, in a rhythm older than human memory. No moon orbits alone. Each one moves inside a web of pulls and pushes, of magnetic fields and radiation belts, of sibling moons that tug on each other across the long, quiet dark. To ask whether a moon hides life, you have to ask what surrounds it. The neighbors matter. They shape the warmth, the chemistry, the very shell of ice that might be hiding an ocean below. Ganymede sits inside one of the strangest neighborhoods in the solar system. It circles Jupiter alongside 3 other large moons, each one round and bright and full of its own quiet questions. Io burns with volcanoes closer in. Europa glides between them with its cracked white shell. Callisto drifts farther out, dark and pocked and old. Ganymede holds the middle ground, the largest moon in the entire solar system, larger even than the planet Mercury. What makes Ganymede strange is not just its size. It is the only moon we know that makes its own magnetic field. A magnetic field is the invisible shape a world casts when something deep inside it stirs and flows. Earth has one. Jupiter has a huge one. Most moons have none at all. Ganymede has a small, gentle field of its own, tucked inside the much larger field of Jupiter, like a soft glow inside a bonfire. That little magnetic whisper is one of the strongest hints. We have that something liquid moves inside this moon. Spacecraft passing close to Ganymede have measured a faint wobble in its magnetic signature. The wobble seems to match what you would expect if a deep, salty ocean were sloshing beneath the ice. Salt water conducts electricity. When Jupiter's huge magnetic field sweeps past, a conductive ocean would push back gently, and that gentle push is what the instruments seem to feel. That is one theory, and it is the leading one. There is another possibility worth holding onto. The wobble might come from motion deep inside the moon's rocky core, not from a buried sea. Most researchers favor the ocean reading because the numbers line up so well. But the other idea has not been ruled out. We are still listening to a whisper, and whispers can be misheard. The neighbors hear matter in another way too. Ganymede, Europa, and Io are locked into a slow rhythmic dance called orbital resonance. For every 4 loops Io makes around Jupiter, Europa makes 2, and Ganymede makes 1. Their gravity tugs on each other in steady, repeating beats. Those tugs squeeze and stretch the moons as they move, and that squeezing makes heat. Without that dance, Europa might be a frozen, lifeless ball. Without that dance, Ganymede's deep ocean might already have turned solid. So the question of life on any single moon cannot really be answered by looking at that moon alone. You have to look at its siblings. You have to look at the giant planet they all circle. You have to look at the resonance, the magnetic field, the radiation belt that bathes them all in invisible energy. Each piece holds up another. Jupiter's radiation is another part of the neighborhood. It is fierce, much stronger than anything around Earth. It scours the surfaces of the inner moons and breaks apart molecules in the ice. On Europa, that radiation might actually help by making oxygen-rich compounds at the surface that could one day filter down into the ocean. On Ganymede, the magnetic field deflects some of that radiation away, giving the surface a slightly calmer existence. Whether that helps or hurts the chances of life below is still an open question. A calmer surface means less mixing of chemistry between the outside and the deep water. A harsher surface might deliver more food, but also more damage. There are smaller neighbors too, small moons closer to Jupiter that no one talks about much. Dim, irregular shapes that came from elsewhere and were captured long ago. The system is crowded in its own slow way. Dust, charged particles, faint rings, all of it part of the same machine. When we picture a moon that might hide life, it is tempting to picture it as a lonely ball in the dark. The truth is gentler and more tangled. These moons live in families. They lean on each other. Their heat, their oceans, even their magnetic voices are partly gifts from the bodies nearby. Whatever is, or is not, swimming inside Ganymede's deep saltwater layer, owes its existence to a dance that has been going on for billions of years, and may go on for billions more, long after we have stopped wondering and gone to sleep. Of all the large moons of Jupiter, Callisto is the quiet one. It does not flash with volcanoes like Io. It does not crack and shift like Europa. It does not pulse with a strong magnetic field like Ganymede. Callisto simply waits. It has been waiting for a very long time, and that patience is part of what makes it strange. Callisto holds a record that is easy to miss. Its surface is thought to be the oldest unchanged surface in the entire solar system. Some parts of it may have looked nearly the same for 4 billion years. Nothing has wiped the slate clean. No flowing lava, no churning ice, no shifting plates. Each crater that formed on Callisto long ago is still there, sitting where it landed. This makes Callisto a kind of frozen library. Every scar tells a story of an ancient impact, and the scars are everywhere. Callisto is the most heavily cratered world we know. Its surface is so packed with old wounds that new craters often land on top of older ones. In some places, there is no room left for fresh marks. The most famous of these is a vast bullseye called Valhalla. It is one of the largest impact structures in the solar system, spreading rings across the icy ground for nearly 2,000 miles. When the rock that made Valhalla struck, the soft, icy crust rippled outward like water in a still pond, then froze in place. Those rings are still visible today, faint and gray against the dark surface. Callisto is also one of the darkest of the big moons. Its surface reflects only about 1/5 of the sunlight that falls on it. Compared to bright Europa, which gleams like a polished pearl, Callisto looks dusty and worn. Many researchers think a layer of dark rocky material slowly built up as the ice on top sublimated away, leaving the heavier grains behind. The result is a moon that wears its age on the outside, and yet, beneath that quiet skin, something unexpected may be hiding. When the Galileo spacecraft flew past Callisto in the 1990s, it noticed something odd. Jupiter's huge magnetic field seemed to be disturbed near the moon in a particular way. The simplest explanation, some scientists argued, was a layer of salty liquid water buried deep inside. Salty water conducts electricity, and a conducting layer could bend the magnetic field exactly as observed. If that interpretation is right, Callisto joins the list of icy moons that may hide a hidden sea. The ocean would sit far below the surface, perhaps 100 miles down, sandwiched between layers of ice and rock. It would be cold, dark, and almost certainly very still. Whether it could host any kind of life is a much harder question, and one we cannot answer from here. Other researchers are more cautious. They point out that the magnetic signal could have other explanations. A layer of slushy ice or pockets of briny material spread through the crust might also fit the data. Callisto, unlike Europa and Ganymede, does not show clear signs of internal heating. Without a strong heat source, keeping a deep ocean liquid for billions of years is harder to explain. The mystery remains open. What sets Callisto apart in habitability terms is its calm. It sits far from Jupiter, outside the worst of the planet's radiation belts. A future lander on Callisto would face a gentler environment than one on Europa, where the radiation is fierce enough to damage electronics in days. For this reason, some mission planners have looked at Callisto as a possible base for long stays. A quiet moon makes a friendlier neighbor, and yet the very thing that makes Callisto safer also makes it less promising. Less tidal squeezing means less heat. Less heat means less melt. Less melt means less chance of the warm, chemically active water that life, as we understand it, seems to need. Callisto may be a haven for visitors, but a poor home for microbes. So we are left with another quiet contradiction. The oldest face in the solar system, the most patient crust, the most heavily scarred ground, a possible hidden sea, deep and dark and slow. A world that may have all the time in the universe, but none of the warmth. The question of whether Callisto belongs on the short list of moons that might hide life has no clean answer tonight. It hangs there waiting, the way Callisto itself has waited. Patient, cold, marked by every old impact, and quietly holding, perhaps, a secret that no spacecraft has yet been built to read. Far out, past the orange smog of Titan and the soft gold rings of Saturn, past the pale blue rim of Uranus, there is a moon that moves the wrong way. Its name is Triton, and it circles Neptune in a slow backward loop against the spin of its own planet. Almost every large moon in our solar system turns in the same direction as the world it orbits. Triton does not. It glides the other way, quietly, patiently, as if it remembers a different home. That single small detail tells us something gentle and strange. A moon born beside its planet would not move backward. The simplest idea is that Triton did not begin as Neptune's moon at all. Long ago, it may have wandered in from the cold belt of icy bodies that drifts beyond the planets, the same shadowy ring of worlds that holds Pluto and many smaller siblings. Some passing dance of gravity caught it, and Neptune pulled it close. Other ideas exist. A few researchers wonder if a collision near Neptune sent Triton into its unusual path. The question of how exactly it arrived has never been fully settled. What the spacecraft Voyager 2 saw in its single quiet flyby in 1989 was a face unlike any other. Triton's surface is pale pink in places, soft cream in others, with a faint blush of red along its broad polar cap. The colors come from frozen nitrogen and methane, painted thin across the crust. In the long Neptunian winter, gases freeze onto the ground. In the long summer, they lift away again into a whisper of atmosphere. The whole moon breathes slowly across decades. The most delicate detail of all may be the texture of its skin. Across much of Triton, the surface looks like the rind of a melon. Scientists call it cantaloupe terrain because the resemblance is so close. It is a pattern of shallow dimples and ridges, each about 30 kilometers across, repeating gently across vast plains. Nowhere else in the solar system has anyone found a landscape quite like it. One idea is that slushy ice, slightly warmer than the layers above, slowly rose in soft blobs and broke through the crust like wax in a lamp. Another idea is that the surface collapsed in patterns as buried ices changed form. Both possibilities remain open, and the dimples sit there waiting, soft and silent, for someone to look again. There are darker streaks too. Long, thin smudges trail across the bright ice, all pointing in roughly the same direction. They look like shadows of something blown by a slow wind. They may be the residue of plumes, fountains of nitrogen gas and dark dust that Voyager glimpsed rising from the surface, drifting for kilometers before settling back down. If those plumes are still active today, then Triton is one of only a handful of worlds in the solar system that is still geologically alive. The others include Earth, Io, Enceladus, and perhaps Europa. To find such activity on a moon so far from the sun is a small, beautiful puzzle. Triton is also unusually smooth. Its surface holds very few craters, which suggests it has been resurfaced again and again over long stretches of time. Something inside it has stayed warm enough for long enough to refresh its face. Where that warmth comes from is part of the open question. The sun is so faint at Neptune's distance that its light feels more like memory than heat. The warmth, if it exists, must come from within, from the slow squeeze of tidal forces, from radioactive elements buried deep, or from the lingering heat of Triton's strange capture long ago. And then there is the quiet possibility that beneath all this delicate ice, there is liquid water. Some models suggest a salty ocean might still exist below Triton's crust, kept warm by the slow flexing of an orbit that has not yet settled into a perfect circle. Other models suggest any ocean there must have frozen long ago. The numbers depend on details. We cannot yet measure the exact thickness of the ice, the exact composition of the rock below, the exact age of Triton's odd path around Neptune. For now, what we have is a flyby decades old, a few thousand photographs, and a small handful of measurements. The Cantaloupe Plains, the dark wind-streaked Plumes, the backward orbit, the pale pink polar cap. Each detail is a single thread in a much larger picture we have not yet finished weaving. Triton drifts on, the wrong way around its giant blue world, holding its secrets with the patience of something that has been waiting a very long time and may be willing to wait a little longer. Far out at the edge of the solar system, in the cold dark beyond Neptune, there is a moon that should have been quiet. It is called Triton, and for most of human history, it was nothing more than a faint point of light. We discovered it in the year 1846. only 17 days after Neptune itself was found. A British astronomer named William Lassell spotted it through a telescope he had built himself in his own back garden, with the patience of a brewer turned stargazer. For more than a century after that, Triton stayed a mystery. It was too far, too small, too dim. Astronomers could measure its rough size and track its strange backward orbit, but they could not see its surface. They did not know if it was rocky or icy. They did not know if it had an atmosphere. They could only wonder. Then came the long, quiet voyage of a spacecraft called Voyager 2. It launched in 1977, carrying cameras and sensors and a golden record of sounds from Earth. It passed Jupiter. It passed Saturn. It passed Uranus. And in August of 1989, more than 12 years after leaving home, it finally reached Neptune. Its closest approach to Triton came just 5 hours after it swept past the blue planet. It was the last solid world Voyager 2 would ever visit. The images it sent back changed everything. Triton was not a dead, frozen ball. Its surface was pale pink and pale blue, dusted with frozen nitrogen, etched with strange, wrinkled patterns that scientists started calling cantaloupe terrain. There were almost no craters. That meant the surface was young. Something was repaving it. Something inside Triton was still alive in a geological sense, still moving, still changing. And then the team noticed something even stranger in the pictures. Dark streaks. Long, thin smudges on the icy plains, all pointing in the same direction, as if blown by a wind. When they traced the streaks back to their source, they found small dark spots. From those spots, plumes of gas were rising several miles into Triton's thin atmosphere, where high winds caught them and dragged the dark material across the ice. Triton had geysers, active ones, erupting in real time at the edge of the known solar system, on a moon so cold its surface sits at around -235 degrees Celsius. That makes Triton one of the coldest places ever measured anywhere. And yet something was venting through the ice. The Voyager team had not expected this. The discovery was almost an accident. The spacecraft was busy. The encounter was brief, and and the geysers were small features tucked into a flood of new images. It took careful work back on Earth to confirm what the pictures were showing. By the time the announcement came, it was clear that humans had stumbled onto something profound. A frozen moon far from the sun was not asleep. What drives those plumes is still an open question. One idea is that sunlight, weak as it is at that distance, warms dark patches under a clear nitrogen ice cap, building up pressure until the gas bursts free. Another idea is that internal heat, perhaps left over from Triton's strange violent capture by Neptune long ago, is keeping parts of its interior warm enough to drive activity from below. The two ideas point in very different directions. One says the geysers are a thin surface trick. The other says there could be a liquid layer hidden deep inside. That second possibility is what keeps Triton on the short list of moons that might hide life. If there is heat down there, and if some of that heat reaches a buried ocean of water mixed with ammonia, then Triton joins the company of Europa and Enceladus as a place worth wondering about. The evidence is thin. We have only that one brief flyby. No spacecraft has been back since. That is the humbling part of this history. Almost everything we know about Triton comes from a few hours of close observation in 1989. The geysers were seen once by one camera on one passing visit. Nobody has watched them since. We do not know if they still erupt today, or how often, or what the dark material really is. Voyager 2 is now drifting through interstellar space, far beyond Neptune, still carrying that golden record. And Triton keeps turning backward in its slow, lonely orbit, with its pale pink ice and its quiet plumes. It is waiting for us to come back. Whether we ever will, and what we might find when we do, remains one of the open questions at the cold, dim edge of our small, bright sun. Among all the moons of Saturn, Mimas is the one most people would not bother to study. It is small, only about 400 kilometers across, and its surface looks beaten and old. A single enormous crater dominates one side, giving it a strange and lopsided face. For a long time, scientists thought of Mimas as a kind of frozen leftover, a ball of ice and rock that had simply sat in place for billions of years, holding still while its more famous neighbors stole all the attention. That assumption made sense. Mimas shows almost no signs of warmth. Its surface is not cracked like Europa's. It does not spray water into space like Enceladus. It does not glow with strange chemistry like Titan. By every visible measure, Mimas looked dead, cold, inert, a quiet pebble orbiting a giant. Then came the wobble. When scientists studied Mimas closely, they noticed something they could not explain. The moon was not rotating in a perfectly smooth way. It rocked very slightly back and forth as it traveled around Saturn. This tiny rocking motion is called libration, and every moon has some version of it. But the size of the wobble on Mimas was wrong. It was bigger than a solid, frozen interior should allow. Something inside Mimas was moving. For a while, researchers wondered if the moon might have a strangely shaped rocky core. A long, stretched core could explain the wobble without needing anything exotic. That was one theory, and it kept things simple. But careful study suggested the core would have to be a very odd shape indeed, and there was no obvious reason for it to form that way. Another idea slowly took shape. What if Mimas held a hidden ocean beneath its surface? A layer of liquid water, sloshing gently inside the moon, could produce exactly the kind of wobble being measured. The outer shell of ice would float a little freely on that buried sea, rocking in a way that solid rock simply cannot. This idea seemed almost impossible at first. Mimas shows no surface cracks, no plumes, no warm patches. If an ocean really does hide inside it, the ice above must be remarkably smooth and undisturbed, perhaps 20 or 30 kilometers thick. Recent work suggests that if the ocean exists, it may be very young in geological terms, possibly only tens of millions of years old. That is a blink of an eye compared to the age of the moon itself. The question of which idea is correct remains open. Some researchers favor the buried ocean. Others still suspect an oddly shaped rocky interior, or some combination of factors we have not yet pinned down. The data fits more than one story, and the surface of Mimas gives away almost nothing. if the ocean theory is right, it changes how we think about icy moons in general. It suggests that a world can hide a sea inside itself without leaving any obvious clue on the outside. A moon can look completely dead and still have liquid water moving below. That is a strange and humbling thought. It means we may have walked past other candidates in the outer solar system without even pausing to look twice. Consider what this would mean for the search for life. Until now, we have focused on moons that wave at us. Europa, with its red-stained fractures. Enceladus, with its bright plumes. Titan, with its thick orange air. These worlds advertise their interiors. Mimas, if it really does hold an ocean, hides everything. A perfectly quiet face above a perfectly quiet sea. How many other small moons might be doing the same? The solar system holds dozens of icy bodies that we have only glimpsed from a distance. Some are smaller than Mimas. Some are stranger in shape. If a moon this small and this still can hide a sea, then the list of places worth a second look grows much longer than we once believed. The chemistry of any Mimas ocean is also unknown. We do not know if it touches rock at the bottom, where useful minerals might dissolve. We do not know how warm it is, or how salty, or how old in detail. We do not even know for certain that it exists. The Wobble points toward it. The math allows it, but no instrument has yet seen it directly. For now, Mimas sits in its slow orbit, rocking ever so slightly, keeping its secret close. A small gray moon with a great scar on its face, possibly hiding a sea that no eye has ever observed. The surprise it offered us was simple. The universe does not always announce its hidden places. Sometimes it just wobbles very gently and waits for someone patient enough to notice. Out at the orbit of Jupiter, sunlight is a faint thing. The sun looks like a bright star, not a warm disk. Sunlight there is about 25 times weaker than what falls on Earth. By the time you reach Saturn, it is 100 times weaker. At Neptune, it is barely a whisper of light. And yet, beneath the ice of moons in those cold places, oceans may be sloshing in the dark. Liquid water, kept liquid by something other than the sun. This is one of the strangest connections in our solar system. On Earth, almost everything we call life depends on sunlight. Plants drink the light. Animals eat the plants. Even the deep ocean creatures live on snow that drifts down from sunlit waters above. Take the sun away, and the surface of Earth would freeze within months. But the icy moons of the outer planets seem to play by a different rule. They borrow their warmth from somewhere else. That somewhere else is their giant parent planet. Jupiter is more than 300 times the mass of Earth. Saturn is nearly 100 times. When a moon swings around such a huge world, the pull of gravity does not stay even. It tugs harder on the near side than the far side. As the moon orbits, this uneven pull stretches and squeezes the moon's interior. The rock and ice flex like a slow heart, and that flexing makes heat. We call this tidal heating, and it may be the quiet engine that keeps oceans liquid in places the sun cannot reach. Think for a moment about how strange that is. The sun powers the climate on Earth, but on Europa, the climate of the hidden ocean may be powered by Jupiter itself. The giant is both jailer and provider. It locks the moon in a tight orbit. It bombards the surface with radiation. And it also, in a sense, keeps the water warm. One world is held in balance by another, and both are wrapped in the larger gravity of the sun, which holds the whole quiet system together. There are other connections too, ones we are still trying to understand. The orbits of Jupiter's big moons are linked in a delicate pattern. Io completes 4 orbits for every 2 of Europa and every 1 of Ganymede. This rhythm is called an orbital resonance, a kind of slow gravitational music. It keeps their orbits slightly stretched. That stretch is what allows the tidal flexing to continue. Without the resonance, the orbits might smooth out, the flexing might fade, and the oceans beneath the ice might quietly freeze solid. Life, if it exists there, may depend on a dance between 3 moons that began billions of years ago. The same kind of pattern may hold around Saturn. Enceladus and Dione share a resonance. Some researchers think this dance is part of why Enceladus is still warm enough to spray water into space. Others wonder if there is more to the story, perhaps a deeper source of heat we have not yet found. plumes are strong. The tidal math, by some estimates, seems a little weak. The question stays open. There is a humbling thought hidden in all of this. For most of human history, we believed that warmth came from the sun, and life followed warmth, and so life followed the sun. The discovery that moons can stay warm without sunlight changes the picture. It means the zone where life might exist is much wider than we once thought. It is not just a thin ring around a star. It can extend deep into the cold, wherever a large planet and a flexing moon work together to keep water liquid. Some scientists go further and wonder about moons around planets in other star systems. If a gas giant drifts in the cold outer reaches of its system, far beyond what we usually call the habitable zone, it might still warm an icy moon through tides. A world bathed in starless night might still hide a sea. We have no proof of such places yet. The technology to find moons around distant planets is still young. The idea remains a careful guess, one that grew directly out of what we see in our own backyard. So the symphony plays on very slowly. The sun holds the planets. The planets hold their moons. The moons pull on each other in long, quiet rhythms. Heat seeps from this dance into hidden seas. And in those seas, perhaps, chemistry is doing something we cannot yet name. We do not know if life is part of the music. We only know that the music has been playing for a very long time, in places the sunlight barely reaches, and we are just beginning to learn how to listen. Nothing in the outer solar system sits perfectly still. The moons we have been wondering about all night are pulled and stretched and squeezed in slow, patient ways. The force doing the pulling is gravity, the same quiet hand that holds the rings of Saturn and keeps the planets in their lanes. When that hand pulls a little harder on one side of a moon than the other, the moon flexes. And when something flexes, it warms. This flexing has a name. We call it tidal heating. The word tidal comes from the same root as the tides that lift and lower the seas on Earth. The moon pulls on Earth's oceans, and the oceans rise and fall in a slow daily rhythm. Out among the giant planets, the pull is much stronger, and the bodies being pulled are not just water, but whole worlds of rock and ice They bulge slightly toward their planet and slightly away from it. As they orbit, the bulge shifts. The rock and ice rub against itself deep inside. That rubbing makes heat. Europa is a fine example. It orbits Jupiter in a path that is not a perfect circle. Sometimes it swings a little closer to the giant, and sometimes a little farther. Each pass changes the shape of the pull on its body. Europa squeezes and relaxes, again and again, for billions of years. The friction inside warms the layers below the ice. Many researchers think this is the reason Europa can have a liquid ocean so far from the warm sun. Without the squeeze, the ocean might have frozen solid long ago. Enceladus tells a similar story, only smaller. The little moon should be too tiny to hold any warmth inside. By the simple rules of size, it should be a cold ball of ice through and through. Yet its south pole steams gently into space. The likely reason is that Saturn pulls on it just enough, and its neighbor moons nudge it into a slightly stretched orbit, and the constant flex keeps a pocket of liquid water alive. The geysers we spoke of earlier are, in a way, steam from a kettle warmed by gravity itself. How strong the heating is, and where exactly it gathers inside a moon, remains an open question. One idea is that most of the heat builds up in the rocky core, deep beneath the ocean, where the squeezing presses hardest. Another idea is that much of the heat is made inside the ice shell itself. As warmer ice flows slowly and rubs against colder ice, both views are still being tested. The answer matters because it tells us where the warmest, most life-friendly spots inside these moons might be. The slow changes are easy to miss. A moon does not look different from one year to the next. But over millions of years, the path of an orbit can shift. Moons drift outward or inward. They fall into rhythms with their neighbors, where one moon completes 2 orbits for every 1 orbit of another. These rhythms, called resonances, can pump energy into an orbit and keep it from settling into a lazy circle. As long as the orbit stays a little stretched, the tidal squeeze continues and the heat keeps flowing. Yet nothing lasts forever. Resonances can break. Orbits can relax. Some researchers wonder whether the ocean inside Enceladus is a long, steady feature of the moon's life, or a passing phase that lit up only recently in cosmic terms and may fade again. Others suspect the same about Europa. If the ocean comes and goes over long stretches of time, then the window for life to begin and survive becomes harder to picture. Perhaps we are looking at these worlds during a warm spell. Perhaps the warmth has been steady for billions of years. The evidence is incomplete. There is also the matter of what tidal heat can do beyond simply melting ice. It can drive currents in a hidden ocean. It can keep the rocky floor warm enough for slow chemistry. It can crack the shell above, opening pathways between the dark sea and the surface. Each of these small effects could matter to whether anything living might take hold. None of them are proven on any moon we have visited. So the picture is one of slow, patient change. Gravity pulls, moons flex, heat seeps out where we cannot see it. Orbits drift over ages longer than any human story. The worlds that might hide life are not frozen statues. They are living machines of stone and ice, kneaded gently by their giant planets, warmed by a force we cannot feel from where we lie. Whether that warmth is enough, and whether it has lasted long enough, is still a question waiting for an answer. To wonder about life beneath the ice of distant moons, we have to first travel down, not up. We have to sink into the deep places of our own ocean, where the sunlight never reaches, where the water sits black and heavy and still. The pressure there is crushing. The cold is steady. And yet, in this lightless world, something remarkable happens at the seams of the seafloor, where the planet's inner heat seeps out through cracks in the rock. These cracks are called hydrothermal vents. They are openings where seawater slips down into the crust, touches hot stone, and rises back up, loaded with minerals. Some of them rise as tall chimneys, built slowly from the minerals that the water drops as it cools. The water that pours from them can be black, or milky white, or a soft pale gold. In photographs taken by deep submersibles, these chimneys glow faintly in the beams of artificial light, and around them, the rock is covered in life. That is the strange and beautiful thing. Down where no sunlight can ever fall, where photosynthesis is impossible, there are gardens of living creatures, tube worms longer than your arms sway in the warm currents. Pale crabs pick their way across the stones. Shrimp with eyes on their backs cluster near the heat. Mats of microbes coat every surface in soft layers of cream and rust and pale green. They do not need the sun. They feed on the chemistry of the vents themselves, pulling energy from the minerals dissolved in the rising water. This discovery, made in the late 1970s near the Galapagos Rift, quietly changed the question of where life could exist. Before that, many researchers thought sunlight was the foundation that life rested on. Plants caught the light. Animals ate the plants. The whole pyramid stood on a single golden beam from the sun. But the vents showed something different. They showed that an entire community of living things could thrive on heat and chemistry alone, in total darkness, fed only by the slow breath of a planet's interior. The light in that scene is not sunlight. It is the faint glow of mineral-rich water and the soft shine of biology itself. Some of the microbes near the vents produce a dim chemical light of their own. Some of the vents emit a very weak thermal glow, just barely detectable, as if the heat itself were trying to remember how to shine. Researchers have wondered if this dim radiation might even be enough, in some cases, to power a strange form of photosynthesis at the bottom of the sea. The idea is unconfirmed. The evidence is thin. The question stays open. What all of this suggests for the moons is gentle and powerful. If life can take root at the seam between cold, dark water and warm rock here on Earth, then perhaps the same kind of seam exists at the bottom of Europa's ocean, or beneath the salty waters of Enceladus, or deep inside Titan, or hidden under the icy shell of Ganymede. The recipe seems to be simple. You need liquid water. You need a rocky floor. You need heat moving through that rock. You need time. The moons we have been wondering about may have all four. Tidal forces keep their oceans warm. Their cores press against the water below. Their interiors are old. If a vent like the ones in Earth's deep sea opens somewhere on the floor of Europa, no one would see it. No light from the sun reaches that depth. The water above is black. The ice above the water is many kilometers thick. And yet, a chimney could still rise quietly, and minerals could still gather, and the strange chemistry could still begin. Whether life would actually take that opening is the part we do not know. Some researchers think the conditions are enough on their own. That life is almost a natural consequence of warm, wet chemistry given long enough. Others think the path from simple chemistry to a living cell is far harder than we realize, and that Earth may have been lucky in ways we have not yet understood. Both views remain in play. The vents on our own seafloor are evidence, not proof. Still, when you picture them, the dark water, the slow plumes, the soft creatures clustered in the heat, it is hard not to imagine the same scene playing out on a moon you will never visit. A quiet glow at the bottom of an alien sea. A chimney built grain by grain over centuries. And maybe, drifting near the warmth, something small and patient that has been waiting for us to look. Imagine for a moment that you could lower a microphone into the dark water of an alien sea. Not the bright blue ocean of Earth, lit by a warm sun, but a sea wrapped in ice many miles thick, with no sky above and no shore in sight. What would you hear there? The slow groan of ice flexing under the pull of a giant planet. The faint hiss of bubbles rising from cracks in the rocky floor. The soft chime of mineral grains tumbling through currents that no living eye has ever seen. Sound travels well through water. It travels even better through cold, dense, salty water, and the oceans we suspect on Europa and Enceladus and Ganymede may be among the quietest, deepest, most patient places in the solar system. A single low note from a vent on the seafloor might carry for hundreds of miles before fading. The whole ocean could ring very softly, like a bell that no one has ever struck hard. The chemistry of that cold, dark water is the real heart of the mystery. Liquid water alone is not enough for life. Life, as we understand it, needs water plus the right mix of ingredients, plus an energy source, plus time. So researchers ask the same question over and over. What is dissolved in those hidden seas? What molecules drift through them? What reactions might be happening on rocks we cannot see? One idea, supported by samples taken from Enceladus's plumes, is that the water beneath that little moon's ice is salty and slightly alkaline, with hydrogen gas mixed in. Hydrogen is a kind of fuel. Certain microbes on Earth feed on it, combining it with carbon dioxide to make methane and energy. If the same chemistry is happening in Enceladus's ocean, then the building blocks for a simple food chain may already be in place. That is one possibility. It is not proof. A competing view points out that hydrogen and carbon dioxide can react without any life at all. The chemistry is just chemistry. Finding the ingredients does not mean anything is eating them. Some researchers wonder if the Plumes show us a lively kitchen with no cook, a warm pot simmering in an empty house. The question remains open, and a single flyby cannot answer it. Europa's ocean may have a different flavor. Its water is probably salty too, perhaps rich in chlorides and sulfates carried down from the surface. The reddish streaks across Europa's ice hint at salts, and other compounds drawn up from below, then changed by radiation from Jupiter. Some of those compounds, if they cycle back into the sea, could feed reactions that resemble the ones that sustain deep-sea life on Earth. Other researchers suspect the ocean might be too acidic or too poor in certain elements to support much of anything. We simply do not have enough data yet. Titan is stranger still. Its surface seas are not water, but liquid methane and ethane, cold enough to freeze your breath into a stone. Beneath the crust, though, there may be a true water ocean, perhaps mixed with ammonia that lowers its freezing point. The chemistry of that buried sea is almost entirely unknown. It might be gentle and quiet. It might be harsh and lifeless. Two reasonable scientists can look at the same scraps of evidence and reach two different conclusions. And then there is the soundscape we can almost imagine. Picture the slow clicking of ice grains settling against the underside of Europa's shell, like sand falling through an hourglass. Picture the deep thump of a tidal pulse passing through Enceladus, a heartbeat repeated every few hours as Saturn squeezes and releases the moon. Picture on Titan the patter of methane rain against orange dunes, and far below, in dark water no telescope can reach, the silence of a chemistry that that has had billions of years to do whatever it was going to do. We have actually heard a little of this. Spacecraft have recorded vibrations and plasma waves around these moons and translated them into sound. The results are eerie and beautiful. Whistles, long, sustained tones, crackles that rise and fall. They are not voices. They are not signals. They are the natural music of magnetic fields and charged particles brushing against icy worlds. Still, when you listen, it is hard not to feel that something is being said, even if no one is speaking. The chemistry of cold, dark water remains, for now, a quiet puzzle. We know the ingredients are plausible. We know the energy is plausible. We do not know if anything has woven those threads into a living pattern. The ocean does not tell us. It only hums and waits and keeps its secret one more night. Imagine for a moment a small machine resting on a sheet of ice far from the sun. It is the size of a kitchen table, four-legged, patient, drinking power from a slow nuclear battery. Above it, Jupiter hangs huge and banded in the dark sky, or Saturn glows behind its rings, depending on which moon we have chosen. The lander has just touched down, and now the quiet math begins. Every step of its mission rests on numbers worked out years before it left Earth. The flight path was a thread of arithmetic stretched across the solar system, bending past planets to steal a little of their motion. Engineers call this a gravity assist. The lander did not fight gravity. It rode it like a leaf carried on a slow current, arriving at its target moon with almost no fuel left to spare. The orbits of these moons are beautiful in how exactly they repeat. Europa circles Jupiter once every 3.5 days. Io, closer in, circles twice in the same time Europa circles once. Ganymede, farther out, circles once for every 2 Europa loops. This tidy chain of 2-to-1 ratios is called an orbital resonance. It is one of the most elegant patterns in our solar system. The moons tug on each other in a steady rhythm, and that rhythm flexes their interiors, and that flexing makes heat. The math of their dance is also the math of their warmth. A lander on Europa would sit on ice that may be 10 to 30 kilometers thick, give or take, with an ocean beneath that twice as deep as every ocean on Earth combined. Those numbers are still uncertain. Different models give different answers, and the real value waits for measurement. The lander would carry a small seismometer, a quiet listener that feels the moan of ice shifting under tidal stress. From the speed of those tiny vibrations, mission scientists could solve for the thickness of the shell. The ice itself becomes a kind of musical instrument, and the math reads its tone. Other instruments would sample the surface. A scoop, a tiny oven, a spectrometer to break light into its colors. Each color a molecule gives off is like a fingerprint. Amino acids, salts, simple sugars, fragments of fatty membranes. Any of these would shift the conversation about that moon overnight. The lander does not need to find a swimming creature. It only needs to find the chemistry that life leaves behind. One theory says such chemistry would be obvious if it exists. Another says the surface radiation on Europa, fierce from Jupiter's magnetic field, would have shattered delicate molecules long ago. Which view is correct, we do not yet know. On Enceladus, the numbers shift. The ice may be only a few kilometers thick near the South Pole, and plumes of vapor rise hundreds of kilometers into space at speeds close to 400 meters per second. A lander there could simply wait with its mouth open, in a sense, and catch the spray. Each grain of ice would be a tiny letter from the sea below. The mass spectrometer on board would weigh each molecule against a known scale, atom by atom, and from those weights infer the recipe of an alien ocean. Titan is a different problem entirely. Gravity there is about 1/7 of Earth's, and the atmosphere is 4 times denser than ours. A lander would fall slowly, drifting through orange haze for hours. The numbers favor flight. In fact, a small rotorcraft could lift off in that thick air with very little effort, hopping from dune to dune, sampling the strange chemistry of a world where the rain is methane and the rocks are made of water, ice as hard as granite. There is a deeper elegance in all this. The same gravitational equations that Newton wrote down centuries ago still describe these distant arrivals to within a few meters. The same laws of chemistry that govern a kitchen on Earth govern the salt in a buried sea on Europa, the universe seems content to use a small number of rules in a great many places. That economy is part of what makes the search feel possible. We are not looking for magic. We are looking for the familiar in an unfamiliar setting. What a robot lander might find in the end depends on which moon we choose, and which question we ask, and how much patience we bring. The arithmetic is honest. It tells us where to go and when to arrive. It does not tell us what we will see. That part still belongs to the slow, soft mystery beneath the ice. Even now, while you rest, there are spacecraft moving through the dark. They drift between worlds slowly, patiently, on long curving paths that were planned years before they launched. Some have already arrived. Some are still on their way. Each one carries a quiet hope inside it. The hope that, if life is hiding beneath the ice of some distant moon, we might catch a glimpse of it within our lifetime. One of these travelers is on its way to Jupiter. It carries cameras, antennas, and instruments that can sniff the thin gases above an icy surface. Its mission is to look closely at Europa, that cracked white moon with the ocean beneath. It will pass near Europa again and again, swooping low over the ice, listening for signals from the deep. It cannot drill through. It cannot land safely just yet, but it can map the shell, measure the salt, and search for tiny puffs of vapor escaping into space. A second mission, sent by a different space agency, is also bound for Jupiter. It will study 3 of the giant moons with a long, patient gaze at Ganymede. It plans to settle into orbit around Ganymede itself, the first time any spacecraft will orbit a moon other than our own. From there, it will study the magnetic field, the buried ocean, and the strange icy crust. What it finds may answer some questions and raise many more. These missions are gentle. They move slowly. They cannot rush because the distances are huge and the fuel is small. A journey from Earth to Jupiter takes years. Even with the help of gravity from other planets, the spacecraft swing past Venus, past Mars, past Earth again, picking up speed each time, like a child on a long swing. The balance of these missions is fragile. A small error in the math, a small bump from a stray particle, path could drift. Engineers on Earth watch every move with quiet care. They send tiny commands across the dark, and they wait many minutes for an answer to return. Speaking with a spacecraft near Jupiter is a slow conversation. You say something, you wait, you listen, you wait again. There is another kind of balance these missions must protect. We do not want to bring Earth life with us. Even a single hidden microbe tucked into a corner of a spacecraft could ruin our search. If we found life on Europa, we would need to be sure it was truly from Europa and not a stowaway from home. So the spacecraft are cleaned carefully before they leave. They are baked, wiped, and built in special rooms with filtered air. At the end of their missions, some are sent to crash into places where contamination would matter least. This care reveals something tender about the whole project. We are reaching out, but we are also trying not to disturb. We want to know, but we do not want to spoil what we might find. It is a strange, new kind of politeness, practiced across hundreds of millions of miles. Other missions are still only ideas, sketched on paper, argued over in long meetings. One concept would send a small craft to fly through the plumes of Enceladus, scooping up the spray and studying it in flight. Another would drop a lander onto Titan, perhaps a small flying machine that could hop from one strange landscape to another. There is even talk of someday sending a probe that could melt slowly through the ice of Europa and swim in the ocean below. None of these plans are certain. Budgets shift. Priorities change. The path from idea to launch is long, and many good missions never leave the ground. How fragile this all is. The right people, the right funding, the right rocket on the right day, the right weather, the right calculations down to the smallest decimal. One missing piece and a mission can be delayed for a decade, and yet somehow, against all those odds, spacecraft are out there right now, gliding toward icy worlds. What they will find, no one yet knows. They may return data that points clearly toward life. They may return data that suggests the oceans are sterile, quiet, empty. They may return data that is simply confusing, and that takes many more years of study to understand. The question itself remains open, hanging in the cold dark between planets. tonight, it is enough to picture them. Small machines, far from home, sailing slowly through the silence, carrying our curiosity, carrying our questions, carrying the soft, stubborn hope that somewhere beneath the ice, something else is alive, waiting to be noticed. There is a quiet puzzle at the heart of all this wondering. We can send a spacecraft across the dark gulf between planets. We can guide it past rings and shepherd moons. We can teach it to fall into orbit, to snap pictures, to sip the thin gases above an icy world. But we still face a problem that no amount of cleverness has yet solved. How do we know what lies beneath a frozen shell without actually touching the water below? The ice on Europa may be many miles thick. On Ganymede, thicker still. On Enceladus, thinner in places, but guarded by fractures and pressure, and a long fall into the dark. Drilling through that ice is not a small task. It would take a machine able to melt downward for months, or perhaps years, while staying alive in the cold. It would need to send signals back up through a tunnel that refreezes behind it. No spacecraft has ever done such a thing. The closest we have come is imagining it on paper. So we look for shortcuts. We try to read the ocean from the outside. The plumes of Enceladus offer one path, because the moon kindly throws its inner water into space, where a passing probe can taste it. But a single taste is not the same as a long study. The molecules that drift up through those vents may be changed by the journey. They may freeze, break apart, or recombine before they reach a waiting instrument. Even if we find something interesting, we cannot easily tell whether it formed in the ocean, in the ice above it, or in the spray itself. Europa may release Plumes too, though the evidence remains thin and the sightings rare. If those plumes are real and frequent, future missions might fly through them in the same way. If they are not, then Europa keeps its ocean entirely sealed, and we must read it through the ice. That reading is hard. We can measure how the magnetic field bends around the moon, which hints at salty water below. We can map the surface and look for places where the shell has cracked, churned, or thinned. But none of this tells us whether anything is alive down there. It only tells us where life could be possible. Then there is the question of what to look for. life on another world might not leave the same fingerprints as life on Earth. It might use different molecules to store its information. It might build its bodies from chemistry we do not yet understand. A detector tuned to find familiar shapes could pass right over a strange one without noticing. Some researchers argue we should look only for biology like our own, because that is what we know how to recognize. Others argue we should design broader tests, ones that look for any pattern at all that seems too ordered to be random. Both views have merit, and neither has yet been fully tried. There is also a quieter problem, one that few people talk about. Even if we found something, how would we be sure we had not brought it ourselves? Spacecraft are cleaned with great care before they leave Earth, but no cleaning is perfect. A single hardy microbe tucked in a seam could survive the cold and the radiation. If our lander then detected life, we would have to ask whether the life was native or a stowaway. This worry is part of why missions to the most promising moons are designed to avoid the ocean entirely, at least at first. We do not want to contaminate a world before we understand it. So we are left with a curious situation. The most interesting places in the solar system are also the hardest to study, and the hardest to study without changing them in the process. Every method we have is partial. Flybys give us hints. Orbiters give us maps. Landers, if they ever arrive, would give us a tiny window onto a single patch of surface. None of these can answer the deepest question on their own. Some scientists believe the answer will come slowly, through many missions over many decades, each one adding a small piece. Others wonder if a single clear signal could arrive sooner, perhaps from a plume rich in the right kind of chemistry. Both paths remain open. Neither has been walked yet. And so the moons keep their secrets, not because they are hiding them, but because we have not yet built the tools or the patience to ask the question in full. The ice waits, the ocean waits, and somewhere in the long quiet between our world and theirs, the answer waits too, for whoever is willing to keep looking. When we picture life on another moon, our minds tend to draw from what we already know. We imagine small creatures swimming in cold water, drifting near warm vents, feeding on minerals that rise from the rock below. That image comes from our own deep oceans, and it is a good place to start. But the moons that might hide life are not Earth. They have their own chemistry, their own pressures, their own slow rhythms. Whatever lives there, if anything does, may not look like anything we have ever pulled from a pond or pulled from the sea. Some researchers wonder whether life on Europa or Enceladus would resemble the simple microbes we find in our own dark places. Tiny single cells feeding on hydrogen, breathing in sulfur, drifting through salty water that never sees the sun. That is the safer guess, because we know such life is possible. We have found it in the deep crust of our own planet, in volcanic vents, in pockets of brine beneath the ice of Antarctica. If life began the same way on those moons, it might still be small, still be slow, still be hidden in the dark. Other researchers wonder if the answer could be stranger. Titan, with its lakes of methane and ethane, sits at a temperature so cold that water itself is frozen as hard as rock. If anything lives there, it cannot use water as the liquid inside its cells. It would need something else. One idea is that Titan's life, if it exists, might use liquid methane the way we use water. Its cells might be built from very different materials, with very different chemistry. It might breathe hydrogen instead of oxygen, and exhale methane the way we exhale carbon dioxide. The question of whether such chemistry can truly build a living thing remains open. We have never seen it. We are not even sure it is possible. A competing view holds that life needs water, and only water, because no other liquid offers quite the same gentle balance of dissolving and holding together. Water lets large molecules float without falling apart. It bends around them, supports them, helps them find each other. Methane and ethane do not behave this way. They are slipperier, simpler, less generous. By this view, Titan's surface lakes are beautiful but empty, and any life on that moon would be hiding deep inside, where a buried layer of liquid water may still exist. The mystery deepens when we think about time. 1,000,000 years from now, our sun will look much the same to a casual eye. 1,000,000,000 years from now, it will not. The sun is slowly growing brighter, slowly warming, eventually, in several billion years, it will swell into a red giant, large enough to swallow the inner planets. Earth's oceans will boil away long before that. The moons of the outer planets, however, may have a different fate. As the sun grows, the cold places of the solar system will warm. The icy shells of Europa and Enceladus and Ganymede may begin to melt from above. Titan's frozen surface may turn to slush. For a brief window, geologically speaking, these distant moons may become the warm worlds of the solar system. If anything lives in their hidden oceans now, that future warming might give it a chance to spread, or it might destroy it. The chemistry that works at deep cold might fail in the new heat. The slow, steady patterns of pressure and salt might break. Whether any of these worlds will become more habitable or less as the sun changes is one of the long, open questions about the future. Even further ahead, the sun will cool into a small white ember, and the outer solar system will fall into a deeper darkness than it has ever known. The oceans of Europa and Enceladus may freeze through, all the way to the core. Titan's lakes may turn solid. Any life that managed to hold on will face a cold that no microbe on Earth has ever survived. And yet, some researchers wonder whether life, once it begins, can find ways to persist that we cannot yet imagine. Cells that slow themselves nearly to a stop. Chemistry that runs at the speed of stone. We do not know. We cannot know. The moons we are watching tonight will outlast us, and their secrets may outlast our species too. Whatever lives or does not live in those hidden seas, the answer will move at its own pace, indifferent to our questions. For now, the ice holds its silence, and the dark water beneath it keeps its long, slow patience, waiting for a future none of us will see. Step back now, as far as the mind can travel. Picture the whole solar system at once, a small bright sun at the center, the rocky inner worlds drawn close to its warmth, and then the giants further out, each one wrapped in its own quiet family of moons. We have spent these hours wondering about a handful of them: Europa, Enceladus, Titan, Ganymede, Callisto, Triton. A few names, a few faces, but our sun is only one star among hundreds of billions in our galaxy. And our galaxy is only one among the trillions we can see. Most of those stars likely have planets. Many of those planets likely have moons. The math becomes hard to hold in the mind. If even a tiny fraction of those moons carry hidden oceans beneath shells of ice, the number of possible hidden seas in the universe becomes almost beyond counting. We have looked closely at 6 or 7 candidates in our own neighborhood. Out there, beyond the dark, there may be billions we will never visit, never name, never see. Some of those moons may circle gas giants warmed by tidal forces, just like our own. Some may orbit cold dwarf stars, tucked in close, sheltered from harsh light. Others may drift through space with no star at all. Orphan worlds carrying their warmth from within. One idea is that rogue moons, torn loose from their planets long ago, could still hold liquid water deep beneath thick crusts. Another view holds that without a parent world to flex them, such moons would freeze solid all the way through. We do not yet know which picture is closer to the truth. What feels strange and beautiful is that we are made of the same stuff as all of it. The iron in your blood was forged inside ancient stars that lived and died long before our sun was born. The calcium in your bones was scattered across space by supernovae, the violent endings of giants that burned out billions of years ago. The oxygen you breathe right now, the carbon that makes up your skin, the nitrogen in every cell, all of it was cooked in stellar furnaces and flung outward when those stars came apart. You are stardust that learned to wonder. And so are the moons, the ice of Europa, the salt in the spray of Enceladus, the methane lakes of Triton, the deep buried oceans of Ganymede. All of it came from the same cosmic kitchen. The atoms in a possible Europan microbe, if any such creature exists, would be cousins to the atoms in your hand. We share an origin with every world we have wondered about tonight. The same physics, the same chemistry, the same patient assembly of simple parts into something more. This is part of why the question matters so quietly. If life took hold in one of these hidden seas, it would tell us that the universe is in the habit of waking up. That given water, warmth, and time, atoms tend to organize themselves into something that breathes, something that feeds, something that responds to its world. If life did not take hold in any of them, that too would be a deep answer. It would suggest that the leap from chemistry to biology is rare and precious, perhaps even unique to our small blue planet. Both possibilities are humbling in their own way. Neither has been ruled out. Both remain open. Think of all the moons we have not yet imagined. Around stars too faint to see with the eye. Around planets we have not yet detected. Around suns that have not yet been born. The universe is still making new worlds tonight in clouds of dust and gas 1,000 light years away. Somewhere out there, a moon is being born that will, in 1 billion years, hide an ocean of its own. We will not be here to see it. No one we know will. But the process continues, slow and patient, indifferent to whether anyone is watching. And yet someone is watching. You are. From a small, warm room on a small, warm world, you are turning the question over in your mind as you drift toward sleep. That alone is something the universe seems to allow, pockets of matter that can sit with the question of what other matter might be doing on other worlds, in other seas, under other skies. We do not know how many hidden oceans there are. We do not know how many of them are quietly alive. The wondering is the part we get to keep. The answers, if they come, will come slowly, one careful measurement at a time. And so we come to the quiet end of our long wandering through the icy moons of our solar system. We have stood in our imagination on the cracked plains of Europa, where a hidden ocean rolls in slow tides beneath a frozen shell. We have watched the silent plumes of Enceladus rise into the dark, throwing salt and dust toward the rings of Saturn. We have drifted above the orange haze of Titan, where rivers of liquid methane carve their patient paths through fields of ice. We have looked at Ganymede and Callisto and Triton and even tiny Mimas, and we have wondered at each of them in turn. None of these worlds has given us an answer. Not yet. The great question we began with still hangs in the dark, open and unhurried. Which of these quiet moons, if any, hides something living beneath its ice? And how, from so far away, could we ever truly know? Some researchers feel most drawn to Europa, with its young surface and its salty sea. Others place their hopes on Enceladus because its plumes carry the ocean up to us, ready to be tasted by a passing probe. Still others wonder about Titan, where the chemistry is so strange that life, if it exists there, might not resemble anything we have words for. Each idea has its champions. Each idea has its doubts. The honest answer for now is that we do not know. That not knowing is a beautiful thing. It means there is still something waiting. It means the universe has kept a few of its secrets for the people who come after us, and perhaps a few for us as well. Picture, as you rest, a single moon turning slowly in the dark. Its surface is pale and cold, scored with faint blue cracks, lit only by the distant glow of a giant planet hanging above its horizon. Beneath that quiet shell, an ocean moves. It has moved for billions of years. It rises and falls with the pull of its parent world. It carries warmth from deep below, where the rocky floor meets the water, and it spreads that warmth in slow, patient currents. Nothing rushes there. Nothing has ever rushed there. Time on such a moon is measured in the soft drift of mineral grains settling toward the seabed. Far above, the stars wheel in their old familiar patterns. The giant planet turns through its bands of cloud. Other moons pass by in their long orbits, each one a small world of its own, each one keeping its own quiet secrets. And further out, beyond the edge of this small system, the galaxy itself turns, slow as a great wheel of light, carrying everything it holds in one long, graceful spiral. You are part of that turning. So is the bed you are resting in. So is the air around you, and the breath moving softly in and out of your chest. The same atoms that drift in the oceans of Europa drift, in their own way, through you. The same patience that shapes the cracks on Enceladus shapes the slow rhythm of your sleeping mind. The universe is enormous, and you are small inside it, and that smallness is a gentle thing. You are not lost in the dark. You are held by it. Somewhere, perhaps, a robot is already drifting toward one of these moons, carrying our questions across the long, cold distance. Somewhere a scientist is asleep, dreaming of the data that will arrive years from now. Somewhere, beneath an ice shell we have never touched, something may be moving in the dark water. Or perhaps nothing is. Perhaps all those oceans are silent and empty, and the silence is its own kind of answer. We may learn the truth in our lifetimes. We may not. Either way, the wondering itself is a gift. So let the question rest now, the way the moons rest in their long orbits. Let the ice keep its secret a little longer. Let the plumes rise and fall without our watching. The answer will come when it comes, and we will be ready, or someone after us will be ready, and the universe will not mind the wait. For tonight, it is enough to have wandered among these quiet worlds. It is enough to have wondered. It is enough to drift, small and warm, beneath a sky full of moons we have not yet understood. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.